This clip from MIT shows two parallel wires next to each other and current passing through, and they actually force on each other. I encourage you to look this up on YouTube to see that. So now we're going to talk about what happens with two wires and how they're forced with each other. The lab that we do in class, gives practice to getting the intuition with this, so it'll be important to do that if you missed this lesson. But if the current is going in the same direction, those wires are going to be forced together. If they're going the opposite direction, then those two wires will be forced apart. The reason this is because each wire is creating a magnetic field, and then the other wire has current, right? So, this wire right here, I2, has current going this way, and you could take your right hand rule and wrap your fingers around it, and this is going to create a magnetic field surrounding it like this, right? Going in a loop around like this. And so, including when it hits over here. And then we'll try to draw that. So when it hits here, right, it's going to be coming out of the page. And so if you do the other right-hand rule, the FIB, you're pointing to the ceiling, your middle finger's coming at your face, and then you'll see that your thumb is going to the right. And so and likewise, the other wire 1 is going to be producing a field that's going to hit the other wire and then force it as well. So with the SI units, it's important to know the SI units and know what the fundamental units are. We've talked about all of these, the meter, the kilogram, the second, Kelvin for temperature, mole for amount of mass that we have in a gas. And candela, we actually use lux, or going to use lux as we go in the future with look into this, but candela is the SI unit. And the amp, it turns out, the ampere is the unit of electric current. It's defined as that current which, when flowing in two parallel conductors 1 meter apart, produces a force of 2 times 7th newtons on a length of 1 meter. Now, why in the world did they, establish the ampere this way? Well, you remember with the meter, right? We said, okay, with the meter, this is, we have a laser light, and how much time does it take for that laser light to go a meter? That's kind of nice, right? That's a relatively modern thing that prevents us from having to have like a physical, object. Now with the kilogram, le grand que is still the official kilogram, and it's locked in a vault, right? And there's copies of it. They're still trying to figure out a way to make a non-physical object for the SI unit of mass. And then we have the second. Now we've talked about that too. That's the transition of a hyperfine level of an electron and energy levels going back and forth. What they did with the ampere, it's very, very hard. If we look at current is how much Q over T, right? How much charge in a period of time. It's very, very hard to measure charge. We can do it now, but back then there's no way. They can measure charge very easily. And so what they did is they established this, whereas they said, if we have two parallel conductors, we actually have two wires, and we have current going through them, and they experience this much force, as they affect each other, because we have two wires, and they're producing magnetic fields. They're going to force on each other, and 1 meter is exposed. We're going to define that as an amp, and then we can work our way backwards actually for the coulomb. And so, yeah, and that turned out to be a really helpful way to establish that SI unit. So again, why is the amp not based on the coulomb? Like a coulomb per second or something. Again, it was very difficult to measure, charge, and so it's much easier to measure force on wires. And if you send a certain amount of electricity through them, they could physically measure that force, and so that was very helpful. So in terms of the SI base units, the coulomb then is the equivalent of 1 amp second or ampere second. So we have current is equal to Q over T, right? So if we cross multiply, current times time, that's going to equal this. So let's say, you know, you have 1 coulomb in 1 second that passes by. That's going to be 1 amp, and that's what a, you know, a coulomb is a 1 amp second. All right, so here is a conducting wire, and we have current that's going around based on that black arrow there. And this is trying to show this three-dimensionally. You know, the wire is coming out of the page and then into the page. And what happens is with this is if current's passing like that, and you grab that wire with your right hand, and we do this in class, probably the best thing that you could do if you can, if you want to grab like a roll of masking tape, this could be really good. And then you could just hold it like on like you see on the screen. So if you hold the masking tape, and feel free to pause the clip and grab one. This will help you with definitely help you with the visual here. If you grab the masking tape and you grab it with your right hand, and your thumb is pointing in the right hand direction, you'll see how your fingers pass through the middle, and those are representing those blue arrows passing through the middle and then coming around. And that's actually what happens with a magnetic field inside a current conducting wire, and that's in a loop here. And so that's that orientation. And outside of the wire, it's going the other way. But the blue lines, the blue dots here represent that the field going, you know, through the middle here. So this may be easier as well. You have this wire that you can see on the right-hand side. The field is coming out of the page. If you take your piece of tape and, you know, grab the bottom of it, you'll see your fingers coming at your face, and your thumb is going to the right. And, you know, you can move your hand all the way around the direction of the current, and you'll see that your fingers are still coming out of the page. And so hopefully you can visualize that okay. So what a solenoid is when you have a wire, and just like we just saw there, and you have current going through it, and, you know, this solenoid will produce a magnetic field. You may have heard of the term electromagnet, and that's exactly what happens. You have electricity going through a wire, and that creates a magnetic field. And so you don't actually have a permanent magnet, you know, like an iron magnet, but you have this wire with the current passing through, and the magnetic field is produced there. Air core solenoids have nothing inside of them. Iron core solenoids are filled with iron, and so, you know, you have a wire that's wrapped around. So if you have that, right, if you have, let's say, like an iron nail like this, and you wrap it with wire, and you put some current through it, so, you know, this is the positive side, this is the negative side, current's going like this, and as current goes, it's going to wrap around, right, and you're going to create a magnetic field. This will actually create a magnetic field going north like this, and this will look just like a bar magnet, and it can act just like a bar magnet. And in fact, a lot of times whenever you see the use of magnetic fields, a lot of times they're used like that, where, you know, you have your you know, your iron core, or whatever it is, or even just wires, and create, you know, it's creating that magnetic field.